the geometry that relates the dual problem to the primal problem. First, let's review planes from Calc 3. In particular, planes that aren't vertical, but take coordinate lines, we'll lift them onto the plane, I get lines. Z is the equation of a line in point-slope form in either coordinate. And now I'm just going to rewrite it in a more vector-friendly format. We'll use this schematic. The vertical line is a real number. Horizontal line, vectors, because we'll be looking at the graphs of vector functions. This then motivates our definition for Rn. This is the equation of a non-vertical hyperplane in Rn+1. B and C are vectors in Rn, alpha and beta, real numbers. Because I have slope numbers, it's non-vertical. We want to look at a bunch of optimization problems where we'll change the constraint. So we're starting at B and then we'll change it to some other right-hand side, and we'll get our optimum function value for that right-hand side. That's that phi function. If my hyperplane and the phi function have this relationship, where the plane is always below the graph, then this hyperplane is called a supporting hyperplane. Of the set of points above the graph. With that lambda fixed, I want to raise the plane up until it hits the graph. The height above B, I'll call that beta sub lambda. Beta lambda is the maximum beta value that maintains the supporting hyperplane condition. Plugging in C equals B, beta lambda is less than or equal to phi of B. My claim is that the dual problem is really maximizing beta lambda over all lambda. This maximum supporting hyperplane looks something like this. Plugging in the point B, that number is still going to be less than phi of B. What we'll show next is that beta lambda is g of lambda, the dual function. Start with our supporting hyperplane condition. I'll rewrite it to highlight the dependence on C. Take all the C terms to the right-hand side. beta is a lower bound. So if I take the infimum over all C, that number is the greatest lower bound, the supremum of all the lower bounds, which is the definition of beta sub lambda. The supremum, remember, is taking over all betas of the supporting hyperplane condition. Replacing phi of C by its definition. It's the smallest f value over the constraint set with right-hand side C. We're in that constraint set, so h of x equals C. This is the infimum over all x's. Which is the infimum over all x's of the Lagrangian, the definition of G lambda. We're finally in position to give a geometric condition for a strong Lagrangian. We're dealing with particular kinds of supporting hyperplanes, so we'll give them this name. It's a supporting hyperplane to phi at P. P is then the point of tangency. We will show that this condition is equivalent to saying the optimization problem with right-hand side P is strong Lagrangian. To align notation from before, let's replace P with B. And we'll redraw what this looks like locally. There's the graph of phi. And I have a point of tangency that it's a supporting hyperplane. Replacing beta with phi of b. Let's prove that the supporting hyperplane gives us a strong Lagrangian. Replacing beta with phi of b, we just follow the inequalities down. Phi of b is then less than or equal to g of lambda. But from before, we know that g of lambda is always less than or equal to phi of b. Therefore, they're equal. The problem is strong Lagrangian. For the other direction, given a strong Lagrangian problem, the definition of phi of b, it's equal to g of lambda for some lambda. Writing down the Lagrangian. And then following the string of equalities we just laid out. So phi of b is a lower bound for all the hyperplanes. there's a supporting hyperplane by just taking the lambda term to the other side. And we're done.